Hey guys, so I want to start you off with a quick proof of the chain rule here today. So what we're looking for is we're trying to find the derivative of some function f of x, or f of g of x, and by the chain rule we know that that's equal to the derivative of f evaluated at g of x times g prime of x. Now in order to do that, I'm going to take a look at the first principle's definition of the derivative. So let's write that down now. So the first principle's definition of the derivative is the derivative of a function is equal to the limit as h goes to 0 of f of g of x plus h minus f of g of x. And that's going to be all over h. So this right here is the limit definition of a derivative. So this isn't really going to be helpful to us as it is right now. What I'm actually going to do is I'm going to do something funny and I'm going to multiply by 1. And you're going to say, hey, why multiply by 1? That doesn't do anything. And you're absolutely right. It's not going to do anything. It's just going to help us. Now, the one that we're going to multiply, it's not going to be 1. It's not going to be 3 over 3. It's not going to be something like x over x. It's going to be a little bit more complicated than that. The one that we're going to multiply by, and this is just purely because, well, hey, it works, and as you get better at calculus, as you get better at this sort of thing, you're going to find ways of multiplying by 1 that actually work to be advantageous to you. The one we're going to multiply by is g of x plus h minus g of x, divided by g of x plus h minus g of x. And as you can see, the numerator and denominator are the same, so this will divide through by 1, and everything should work out fine. Put a little caveat here. You have to make sure that everything's continuous. You have to make sure that, hey, when it's evaluated at some number, then hey, it's differentiable on the denominator, because you get some funny things as you divide by 0. But hey, for our purposes, this is going to work perfectly fine. Okay? So one thing that I want to point your attention to is the denominator of both of these. The denominator h and the denominator g of x plus h minus g of x. What we're going to do is we're going to switch these, or switch their positions with each other, because that's going to help us simplify our definition of the derivative in a way that's going to be helpful. So we can rewrite this as the limit as h goes to 0 of, well, we're going to use the same thing up here, f of g of x plus h f of g of x plus h minus f of g of x and like before, we're going to divide through, but since we're switching the bases of the or we're switching the denominators of both of these fractions here, we're going to write on the left hand side g of x plus h minus g of x, and we're going to multiply by, well, the h is going to switch positions over here on the bottom, and the numerator is going to stay the same, g of x plus h minus g of x. And you might say, hey, since we're taking a derivative, since we're looking at limits, well, I know a limit law that says that the limit of a product is the product of the limits. So we can rewrite this as the limit as h goes to 0 of everything here multiplied by the limit as h goes to 0 of g of x plus h minus g of x all over h. You're going to say, wait a second, this is quite simply, or quite strictly, the definition of g prime of x. And yeah, you're right, it absolutely is the definition of the derivative of g prime of x. So we've already knocked off this first part of our proof. So the question is, what about this stuff over here? How are we going to show that the limit as h goes to 0 of all this stuff equal to f prime of g of x? And what I want you to do is I want you to put your attention up here to this little note that's been up here the entire time. We have f prime of a is equal to the limit as k goes to 0 of f of a plus k minus f of a all over k. This is the definition of a limit evaluated at some point a. So if I take a look between this part here and this part here, well, what that tells me is that we're looking at something that says a is equal to g of x. And as long as g of x is continuous at some point a, or as long as it gives us some value, then this substitution is perfectly fine. It's perfectly okay to do. And another thing that I want to do is I want to define some k and kind of take a look at how it acts. Well, if I say that k is equal to g of x plus h minus g of x plus h minus g of x, well, let's take a look at how the limit changes. Well, before we have h goes to 0. So as h goes to 0, how does k act? What does k go to? Well, if we put in 0 here, we get g of x minus g of x. Well, as h goes to 0, k goes to 0 as well. So that's going to change our limit for this part right here. This is going to change how we look at our function. So instead of limit as h goes to 0, we're going to have the limit as k goes to 0. And instead of a, we're going to have g of x. So if we get rid of this question mark here, let's rewrite this as not the limit as h goes to 0, but the limit as k goes to 0. And it's f of g of x plus h. Well, g of x plus h is equal to, g of x plus h is equal to k plus g of x. So what does this equal? Well, this is equal to f of k plus g of x. And we're going to subtract away f of, well, keep this the same, g of x. And we're going to divide by, well, g of x plus h minus g of x. Well, that's simply k from before. So what we have here is, instead of an a, we have a g of x in both situations. So this right here, limit as k goes to 0, is going to be the derivative f evaluated at some g of x. And this is exactly the first part that we were looking for. So what we have in our proof of the chain rule is that if you take the derivative of f of x g of x, and you follow down through taking the first principle's limit and multiplying by 1, then we have shown that the chain rule actually does work. And that is to say that we have f prime of g of x times g prime of x. And there you have it. That is the proof. There's a little box that the chain rule actually works. So if you have any more questions, or if you have any questions about this video, please comment them down below and I'll be happy to respond to you. I know that there is some trickery going on here, but for your intents and purposes, it's probably a okay proof.